Hey engineers, and welcome to 1.2.3, and I believe this is part 4. We're going to be talking about series and parallel today, along with a little something called Ohm's law. So we're going to be building some circuits, and I built one down here, and it doesn't look like much, but we're going to use math, knowing that this is 6 volts right here. And then this is 120 ohms. Can we predict how much current is flowing through this circuit? It doesn't look like much. If you barely watch it, it's moving. And then we are going to look at some series and parallel. So our circuits are going to get a little bit more complicated. I'm going to add multiple resistors, and then I'm going to add multiple resistors in a different way. And how can we predict mathematically how much current is flowing through everything and so on. So that's where we're going today. We're going to be using some math to predict how much electricity is flowing, to predict all of that stuff using some simple properties, I guess you could say. So let's start out here. It says the flashlight shown uses a 6-volt battery, and they have a schematic diagram right here. And there's a bulb, and a light bulb is just schematically like a resistor. And I'm going to change this to 120. So in your, just because my simulator won't let me do 150, so I'm just going to cross this off, make it 120. Just so we can simulate it easily. And it says how much current is going to be drawn. So you'll see that there's this blue arrow. This blue arrow represents the current, and it wants to know how much current is flowing through this circuit. Now, there is a property, it's called Ohm's law. And you saw before that if I were to increase the pressure on the battery, I had more current flow, and if I were to decrease or the resistance, I had more current flow. Well, that's actually what this equation does. So what you do is you put in your voltage, 6 volts, over here for 6. And then I don't know my current. This is the unknown. So I don't know. I'm going to just leave it as the letter I. And then the resistance is 120. So that goes in for over here. So then what I do is I just pull out my calculator and I solve this for the letter I. It's 6 divided by 120. So then I just take my calculator out and I go 6 divided by 120. And it's 0.05. So I equals 0.05 amps. That's how much current is flowing. Now, card-carrying ballers of physics, they will say 50 milliamps. So you move that decimal point 3 places, and this is the exact same thing. You don't have to do that, but just know that 50 milliamps is the exact same thing as 0.05 amps. And let's check it out. Let's go over to our little simulator and see if that's actually what we get. So I'm going to roll over here. I'm going to take my ammeter. And remember, to measure the current, we have to break the circuit. So I'm going to break the circuit, put my meter in here like, oh, there you go, 0.05 amps. What do you know? The math works. The next example that we're going to do is a series circuit. Now, a series circuit is when you hook things up kind of like a choo-choo train. So I have this example right here, and I can't do 220 or 470, so I'm just going to round this to 200, and I'm going to round that to 500. So we've got a circuit that looks like this. We have a 12-volt battery, and then it hooks up to a 200 ohm resistor. So we're going to make this 200. And then we have, instead of 470, I'm going to make this 500. So, and then the other one is 1200. So these are all in a line. So I went over here to our simulator and I created this example. And here it is right here, where this is 200. This is 500 ohms, and this is 1200 ohms. and this right here is 12 volts. So I have this circuit simulated here, and we're going to then use some math to predict how to figure out how much current is flowing through this, and we also want to know what's the voltage at every single one. So you'll see here that it asks me what's the voltage of resistor 1, and it wants to know how much current. So there's quite a few things that I want to know. I want to know voltage around 1, voltage around 2, voltage around 3, and then I want to know the current. So there's like 6 things that this problem is asking for, maybe even 7, because it wants to know the total resistance. So let's get started here. Erase this. So the first step in a problem like this is that you want to find the total resistance. R total. And the total resistance for a series circuit is you just add them all up. So I'm going to add up, I'm going to take 200 plus 500 plus 1200, and that's 1900. So the total resistance is 1900 ohms. So there's the first thing that I wanted to know. The total resistance, 1900 ohms. Now, to find the current flowing through here, this is Ohm's law again. If I want to find the total current running through the circuit, I have to use the total resistance and the total voltage. The total voltage is 12 volts. The total resistance is 1900 ohms. That's what we just found right there. So now I can find the total current. So 12 divided by 1900 is 0.006 amps. Or, if you remember back from a little bit ago, move the decimal 3 places, that's 6 milliamps. So either one of these answers is correct. So that's the total current flowing through here. So in this problem, the current flowing through here is 0.006 amps. And because there's only one tube for the water to be flowing, that water flowing over here is also 0.006 amps. And that water right here is 0.006 amps. And that water right here is 0.006 amps. The current is the same everywhere inside of a series circuit. And I can show you that. I'll go over to our little example. I'm going to pull out, this is a different thing to measure current. It's easier than to use this than it is to unhook a circuit, but this only exists inside of the simulator here. Here we go. 0.006 amps right there. I can come over here, and I also get 0.006 amps. I can come down here, and I also get 0.006 amps. Anywhere I put this, the current is going to be the same because there's only one place for the water to flow. Since there's only one pipe, that means that there's only one place for the water to flow. So, the last thing I'm going to do is I'm going to find the voltage. I'm going to find these voltages. Now, just like I'm going to use Ohm's law again. V equals IR. So if I want to find the voltage of resistor 1, that's what I'm looking for right now. I use the current through resistor 1 and the resistance of resistor 1. Woo! So we already know the current is 0.006. And we know the resistance of resistor 1 is 200. So if you take 0.006 and you multiply by 200, you get 1.3-ish. Now, I rounded this 0.006 when I wrote it on the board, but I kept all the decimal points when I did that. So this one, 1.3 volts. So this up here is going to be 1.3 volts. And let's check it out. Let's go over to our simulator and see if that's true. So I'm going to grab my voltmeter, and I'm going to put this right. I'm going to put my black probe here, and I'll put my right probe right here. 1.3 volts. There it is. Remember, I told you how I did a little bit of rounding, but I get 1.3. It matches to what the math predicts. Let's go back and find the other ones. What is the next one? What's this? Voltage on resistance 2. So we're going to do that Ohm's law again. V equals IR. So if I want to find the voltage of resistor 2, I have to use the current through resistor 2 and the resistance of resistor 2. So the voltage is what we're looking for. The current is 0.006 and the resistance is 500. So if you take 0.006 and you multiply by 500, it's really 3, but remember I did some rounding here, so this voltage of resistor 2 is 3.1. 3.1. Let's check it out on our simulator to see if that's true. Grab my voltmeter, put my black lead down here, put my red lead up here. 3.1. Nice. And then lastly, we'll do our final one, that VR3 right here. So we're going to use Ohm's law one final time. So take 0.006 and you multiply by 1200 and you get 7.6. So this 7.6 volts. Let's go over to our simulator to see if that's true. Voltmeter down, my red lead here, black lead, red lead, 7.6 volts. Now, if you're paying attention, and this is a tricky thing to see. If you look at the total voltage is 12 volts. The voltage around this one is 1.3. The voltage around this one is 3.1. And the other one is 7.6. Believe it or not, 1.3 plus 3.1, that's 4.4. And then 4.4 plus 7.6, that equals 12. So here's some really important ideas inside of a series circuit. In a series circuit, add up the resistors. You're going to take 1 plus 2 plus 3. You're going to add them all together. The current is going to be the same everywhere. You'll notice that I put 0.006 amps everywhere. And then the voltage of each component is going to add up. So this voltage, 1.3 plus 3.1 plus 7.6, these are going to add up to my total voltage, which is 12 volts. A parallel circuit, they're all exactly the opposite. And we're going to see that right now. Our last example is going to be a parallel circuit. Now, here's a schematic. It's 15 volts, and I changed these just to make it easier to use with our simulator. And I made this 40 ohms, I made this 80 ohms, and I made this 120 ohms right here so you could see. And so I made an updated schematic, 40, 80, and 120, and I built it over here on our schematic. Now, there's some key differences here with a parallel circuit. The electricity has a choice. When the electricity comes out of the battery, the electrons come out of the battery, they can go through this resistor, They could B, go through this resistor, or they can C, go through that resistor. And you can see, if you were to look at this wire right here, and if you were to count how many electrons go by in a minute, and you compare it to this one, or you compare it to this one, you'll see that there's a big difference between how many electrons are going through this one, like 1, 2, I mean, I can actually see them going by. It looks like 1 every 3 or 4 seconds. Then you come over here, and they're barely moving. They are moving, but it's really, really slow. You can see it happening up here, just the speed with which they're going through. So more electricity seems to be going through this resistor than this one. And that makes sense because this one's only 40 ohms, and this one over here is 120. It's harder for the electrons to get through this resistor than it is this resistor. Let's look a little bit more in depth at the math here. All right, first key difference in a parallel circuit is the total resistance. The total resistance, you don't just add them up. You go 1 over each of them. For instance, I'm going to go 1 divided by 40 plus 1 divided by 80 plus 1 divided by 120. And that equals 1 over the total resistance. So if I take 1 over 40 plus 1 over 80 plus 1 over 120, you end up getting 0.0045. But this is not the total resistance. I got to take 1 divided by that answer. So my total resistance, take 1 divided by 0.0045, and you get 22 ohms. This is the biggest mistake I see when people do the total resistance. They don't take 1 divided by this answer to get 22 ohms. So my total resistance right over here, 22 ohms. Second key difference is that in a series circuit, the current was the same everywhere, but in a parallel circuit, the voltage is the same everywhere. And I can show that to you on our simulator here. I can bring out my voltmeter, and I can hook my voltmeter up, and it's going to say 12 volt. Or shoot, I'm going to make this 12. 9, 10, 12. It's going to say 12 volts everywhere. So this one says 12 volts. This one over here says 12 volts. And my last one also says 12 volts. Each of these is being pushed on by the battery. The battery is like the pressure. We said voltage is like pressure. If you've ever had like a Play-Doh fun factory where you have a bunch of holes, sometimes you have a really big hole or a really small hole, but they all are getting the being pushed on equally by the clay, and more clay is coming out the one with the bigger hole, which is this case right here. So in this, they all have the same voltage, but so they're all getting the same pressure, but one of these has less kink than the other. This has a very big kink, so only a tiny amount of electricity goes through. This doesn't have a big kink, so then more electricity flows through this one. So with that idea, I'm going to go back to my math, and the voltage here is going to be 15 volts. The voltage here is going to be 15. Shoot, I meant to say it's 15. I meant to go back to my simulation, and I can up that to 15 where it should be. It defaults to 9 volts. That's why I had it there. Last part, we're going to try to figure out how much electricity is flowing through each of these branches. So I'm going to find IR3, the current through R1, and the current through resistor 2. I'm going to use Ohm's law again. V equals IR. So if I want to find the current flowing through resistor 1, Then I have to use the resistance of resistor 1 and the voltage of resistor 1. So the resistance of resistor 1 is 40. I don't know the current, but the voltage is 15. So I take 15, divide by 40, and you end up with 0.375. Or 375 milliamps. For resistor number 2. And let's check that. Let's just go over to our simulator and see if we get 0.375. Bring over my current, and if I put it on this branch, it should say 0.375, and sure enough, it does. Go back to my math. The voltage equals the current times the resistance. And I'm going to now do for R2. So if I want to find R2, I have to use all the values for R2. And you'll notice that 22 that I found before doesn't really get used in this. So the resistance of R2 is 80. The current through R2 is what I'm looking for. And the voltage is 15. So 15 divided by 80. 15 divided by 80 is 0.188. Or 188 milliamps. So IR1, 0.375 amps. Current through resistor 2 is 0.188 amps. And I'll do the exact same thing for my third one. Let's just double check though. So on my simulation, go over here. This should say 0.188. What do you know? It does. Everything seems to be working. So go over to my third one. Ohm's law, V equals IR. If I want to find the current through R3, then I have to use all the values for R3. So the resistor is 120 and the voltage is 15. So this current, 15 divided by 120 is 0.125 amps. So go to my, just check it out to make sure it works. 0.125, absolutely. The last thing I need to find in this problem, it wants me to find the total current. The total current. The total current is going to be adding up. Now here's the third primary difference in a parallel circuit. The current adds up. In a series circuit, the voltage added up, but now in a parallel circuit, the current is going to add up. So I'm going to take each of these currents, add them together, and that's going to give me the total current. And the total current turns out to be 0.69 amps. And remember, that is adding up. I'm taking this one, plus this one, plus this one. Another way I could have done it is by using Ohm's law. But to find the total current, you have to use the total resistance and the total voltage. The total voltage is still 15, and the total resistance, if you remember, was 22. And if you take 15 divided by 22, you get 0.69. So there's another way to get that. And let's roll over to our simulation to just double check to see if that's true. Pow! 0.69. Nailed it. Let's summarize. To summarize a parallel circuit, you don't just add up the resistors. You have to take 1 over the first one, plus 1 over the second one, plus 1 over the third one. The voltage is the same everywhere. and the current adds up. This is exactly opposite of a series circuit. The current was the same everywhere, and the voltage added up. But in a parallel, the voltage is the same everywhere, and the current adds up. I know this was a really long video, and it's so hard to put all of this into one thing that's under 20 minutes. I do appreciate you guys staying with me. Keep your heads up, and let's continue on.